Good. Okay. And I'll just move with you.
I'm there. Hi, my name is Dustin Yanofsky, and I'm going to give you an invitation to category theory. Let me just read. So this is given at Brooklyn College Math Club in, I don't know what day, September 5th, and we're doing it. So the title of the talk is An Invitation to Category Theory. Let me just read the abstract. Over the past few decades, category theory has been used in many different areas of mathematics, physics, and computers. The applications of category theory have arisen, to name just a few: quantum field theory, database theory, abstract algebra, formal language theory, quantum algebra, theoretical biology, knot theory, universal algebra, string theory, quantum computing, self-referential paradoxes, etc. It just shows up all over. I'm sorry, is the air conditioner, you hear me? I'm yelling because I don't want to shut that air conditioner. I need to. Okay, so I'm yelling. The categories are collections of structures and ways of changing those structures. The theory of category has emerged as a theory of structures and processes. Now that's so abstract, what's a structure, what's a process, that it can fit all these different things, okay? So structures and processes, okay? As such, they have been used to describe many different phenomena in mathematics and science. We will describe many basic examples of categories and their related structures. This will help us see why category theory is a unifying language in mathematics, computer science, and physics. The talk is open to anybody. Okay, so the reason why I'm giving this talk is because I came out with this book it's now called Monoidal Category Theory, a unifying concept in mathematics, physics, and computing. Okay, and I got a publisher, MIT Press, and I have to hand it in Thursday, final version, Thursday. So I'm very excited. I'm also very excited about the fact that it's finished, and I can show it off. Okay, just a little thing about this talk. This talk has a prehistory. Okay, I was supposed to give this talk 4 years ago, okay, and COVID came along and knocked out the course. Then about 2 years ago, they said, okay, we're going to start up talks, whatever, and I gave the talk again, and exactly 3 people showed up. So that wasn't very helpful. So this is a talk I've been wanting to give for literally 4 to 5 years, okay, and it's exciting. Okay. 1 second. Wait till you hear the talk. Then you clap.
I couldn't.
Okay. And, I apologize. There's no free pizza, even though I told people there'll be free pizza, but that's okay. You came here for the knowledge. Your brains will be full. Your stomach will be empty. So let me just tell you what we're going to do. This is going to be the world's simplest talk. There's going to be a definition, and then a million examples, and then another definition, and then a million examples. That's it. No theorems, no heavy stuff, no nothing, whatever. So 2 definitions and lots of examples. That's it. But that first definition is going to be the definition of a category, and a category, we're going to give the definition of a category, and then we're going to give lots and lots of examples of categories. So that's good. The second definition is going to be a definition of a functor. A functor is what it sounds like a function. So between sets you have functions, between categories you have functors. Okay? So we're going to give that definition of a functor. The point I'm making is, and we're going to give lots of examples of functor. The point I'm making is, not only do we have a lot of examples of category theories, but we relate them with these functors. Okay, and that's an exciting thing. Okay, so let's start. What's a category? Well, there's different ways of thinking of a category, but I like to think of it as a souped-up graph, simply because we all know what a graph is. So let's remember what a graph is. So a graph is a bunch of dots, vertices, points, and arrows, edges between the points, and things like that. That's a graph. Okay? And we all know a million different examples of graphs. The subway system, the World Wide Web, Facebook, etc., etc. They're all can be mimicked by graphs. Well, categories are graphs, but with more structure. Let me give you an example. Okay? Here, you have an arrow from this point to this point. then you have an arrow from this point to this point. That's fine. That's a graph. Well, within a category, not only do you have arrows, but if you have two connecting arrows, like from here to here and here to here, then there's another arrow connecting them. Okay, so it's a souped up graph. It's a graph with a way of connecting arrows. Okay? That's it. That's it. It has a few more requirements, and I'll be formal with what it is. Okay? That's one way of looking at it. If you know abstract algebra, if you took an abstract algebra class, you know what a group is. What's a group? A group is a set with a way of multiplying elements, okay, bringing together elements. Well, in some sense, I just did that. I have an element here, F, I have an element here, G, and I have, connecting them, I have F control compose G. Okay, so you're taking one thing, you're taking another thing, you're bringing them together. Same type of idea as a group. Okay, so that's what so again, it's a generalization of these two concepts. A graph where you can compose arrows, and a group where you can compose things. So here you can compose arrows. Okay? So let's be a little bit more formal. First, let me give you a formal definition of what a graph is. So a graph is a set V, vertices, and a set E, edges. We're talking a directed graph. And then you have two maps. One we'll call source, and one we'll call target. Okay? So let me just explain to you what it is. This is the set of edges, this is the set of vertices. And so a typical thing here would be this arrow. But the arrows don't just live in the air, they have to come and go from one place, from someplace. So source tells it where it's coming from. So there might be a point here and a point here. And so the source of this arrow could be here, and the target of this arrow could be here, and then we would write it like that. Okay, so this we'll call F for a little edge. Okay, and so we'll say this is F, and then we'll say this is the source of F, where it's coming from, and the target of F, where it's going. Okay? Okay, so that's the definition of a graph. Can't get simpler than that. You have edges, and you have vertices, and the edges go from one vertex to the other. Okay, good. Now we want a definition of a category. Okay, so it's going to be very similar to this. So you're going to have a category C. Okay, so this is look, I'm only giving you two definitions, so you better concentrate on this one. So this is definition one. A category C, that's a bold-faced C, it consists of, just like this, it's going to consist of objects of C. So that's going to correspond to vertices, little things, objects. Okay? And instead of writing edges, I'm going to write morphisms of C. So it's going to have dots and arrows between the dots. Okay? And just like before, but with different names, just like this we call edges and vertices, here we call objects and morphisms, just lots of names. Okay? So we have two functions. Now these are collections. I'm not saying they're a set, they're collections. Okay? And so we have two functions. One is called the domain, okay? And it goes from morphisms of C to objects of C. Okay? Domain is another way of saying source. Where does it come from? Okay? Next is codomain, and it also goes from morphisms of C to objects of C. Okay? So I just gave you a definition of category. 1 second, there's two more parts. Three more parts, whatever. But it's just the same thing as this. You have edges, vertices, two maps between them. You have morphisms, edges, vertices, objects, and two maps between them. but you have something else. Okay? Namely, in a category, you have the following thing. If you have an edge, F, from here to here, so this will be called domain of F to codomain of F. Okay? And you also have a map G from domain of G to this object called codomain of G. Okay? Well, then you have a composition map. Okay? And the composition is written like this: F compose G. Okay? It looks backwards, but it's okay. Okay? Now, I'm going to write something that's a little bit long. Basically, this is a function from morphisms of C cross morphisms of C. You need two morphisms of C, and output, we'll call that composed, another morphisms of C. So you give me one. You give me one. When you give me one morphism, you give me another morphism, you get the third morphism. Okay? But this is not really right, because it's not all morphisms, just those that are connected like this. So I'm going to put the word connected here. Okay? You give me pairs of things that are connected, you can compose them. One more operation. So this is an operation. So this is a function, an operation, one more operation. Something that goes the other way. Identity. This says, you give me an object of C, and I'm going to give you a morphism of C. Let me just explain to you what this is. Here's a typical object. Well, I want a special morphism called identity. So we'll call this X. This is the identity on X. It's a morphism from it to itself. Okay? It's a morphism from X to X. Okay? And it's called the identity. It's a special morphism. And those of you who know what a group is, it's the identity element of the group. It's the thing that does nothing. Okay? So for example, take a number, add 0 to it, you get back the number. Take a number, multiply it by 1, you get back the number. So too here, this morphism is going to be that special unit that does nothing. You'll see why we need it in a second. Okay, great. These three maps have to satisfy some requirements. So this is what we call extra structure. It has to satisfy some requirements. Okay, one requirement is very simple to see. If I have a map here, F, and I have a map here, G, and I have a map here, H, and they come and go from different things, then I can compose these three maps in two different ways. Namely, I can say, oh, look at that. That's F compose G. Okay, good. You know what? In G and H, they're saying that they're connected, they're contiguous. So I can say this is G compose H. Very good. Hold on, I'm finished. But look at this. I now have a map from here to here to here, and then I can, along the same way is H. So I can compose this as follows. This map composed with this map is F compose G, that's this, parentheses, H. 1 second, I have another map. This map is contiguous, it's connected to this. So we say, because this is connected to this, we can compose it, and we get F compose, H compose G. Okay. So here are two maps from here to here. Conclusion, not conclusion. We require that they're equal. Okay, this is called associativity of composition. Okay, we know what associativity of addition is. We know that subtraction doesn't have associativity. This is associativity of addition. Great. That's one requirement. Okay, and one more requirement, then we go to the examples. The other requirement is as follows. here's an element F. It goes from here to here. Now, these two objects, we'll call this X and Y. This has an identity map. We'll call it identity of X. And this has an identity map. We'll call it identity of Y. Okay? What we want is these identities to act like 0 and 1 when we're adding and multiplying. In other words, to do nothing. So we say it as follows, right? If I start here, and I do identity X, so I do identity of X, and I compose it with F, guess what I want to output? So this is a composition. I'm taking this map composed with this map. Well, I want it to equal to F. Don't change it. Okay. Also over here, if I take F and I compose it with Y, so I F composed identity on Y, I want that to equal to F. Don't change it. Submit. Okay. Everyone good? So that's the simplest thing. It's a group, it's a graph because it has these two maps, but it has a little extra, this composition, this identities, and it satisfies, this composition and identity satisfy these two requirements. That's it. Okay? But it turns out that this can deal with a lot of different structures. Okay? Let me just tell you, if you think about it, it can deal with whatever a graph can deal with. Okay? And if you open up any book, whatever, you'll see graphs show up all over. Well, then categories are definitely going to show up all over. But categories can deal with things that graphs can't deal with. For example, with a graph, you can tell when two things are connected. You have a vertex, you have connectivity. So a graph is very good at telling about connectivity. But with a category, you can not only tell about connectivity, you can talk about reachability. We need to explain to you what that means. Let's say you have an object here, and you have another object here, and another object here, and another object here, and another object here. And you want to know, can you go from here to there? Well, a graph can't tell you that. A graph can only tell you what its neighbors are. But a category, if it's got neighbors of neighbors, they become elements too. And so you can talk about reachability. Okay, so that's one way of thinking about categories. Let me give you another way. Okay? Well, groups show up all over. Okay? Groups show up all over. Physics, computers, symmetry, they're all about these things. Well, this is in some sense a group. You have this composition, and the composition preserves the identity. We'll see more. In fact, okay, we're not going to look at that. Okay, good. So, let's start our list of examples. Okay. So, the first example you could possibly think of is the category of sets. Okay. And categories are usually bold-faced, so we have categories. Let me tell you what the objects are. Objects of sets are all sets. Every set you could possibly think of. The set of students, the set of molecules in the air, the set of cool molecules in the air, the set of pizzas that we have in this room. Okay? Those of you on camera can't see it, but we have this luxurious meal here going on. Everybody's stuffing their face. Sorry you weren't here to join us. Okay. All sets. And the morphisms of sets are all functions between sets. Functions between sets. Okay? So you have one function going from a set to a set. So you usually think of a set as, here's the set S, here's the set T, and you have lots of functions between a set. Okay? But you can also compose functions. For example, you can also have the set U, and you can have K and L. These are two more functions. But now we can compose functions. So we can have F compose K. So this is F composed K. And you can have H composed L. Lots of other functions. You have 3 functions here. You have 2 functions here. Then you have 10 different functions. From here to here. No, 6 different functions from here. Okay, great. Composition. Well, we know that function composition is associative, so it satisfies that. But more importantly, there's a little stupid function called ID of u. And there's a little stupid function here called ID of t. And basically, what it says is, if I take, let's take k, if I take the function k, okay, which goes from t to u, and I compose it with ID of u, okay, I compose it with ID of u. So, let's see, what does k go? K goes from t. So I'm going to have a little t over there, and then I'm going to do k of it, and then I'm going to do identity of it. Okay. So this is going to be do k of t, and then do the identity. What's the identity? It's the stupid function that whatever you input, you get the same output. It's a stupid function. ID of u, at the letter little u. Okay, is equal to little u. Can't get a stupider function than that. Doesn't give you any information. Whatever your input is, your output. Okay, so that takes care of that. So we want that if I do k of t, and then I follow it with ID of u, I should get out k of t. In other words, if I take an element here, t, and I do k of it, and then I do that, I still get the element k of t. No change. So what we want these, and then there's another one too. We're going to talk about identity of t. But you know what? You saw enough of that. Okay? The point is that the collection of sets and morphisms form a category. And that's one of the most important categories we will see. Okay, good. I want to talk about some others. Now, how many of you are math majors? How many of you are computer majors? Good. Okay, so we're going to see a lot of different examples. I suspect about half of you will know half of the examples. The rest will learn. Okay? So let me give you another example. If you took abstract algebra, then you know what a group is. If you didn't take abstract algebra, you can still have a good life.
Just not as good.
Just not as good, right? You might be able to get to heaven or something like that, but okay. Okay, so what's a group? A group is a set with structure. Okay, great. But besides group, you can talk about a group homomorphism. So if you have 2 groups, you can talk about a function between those 2 groups. And basically, this function preserves the structure. Let me explain to you what I mean. So if you have 2 elements in here, G and G prime, well, I can multiply them with this group. A group has multiplications. And then I can take f of that. Well, this group also has a multiplication, so we'll call this group G box. So I also can just look at f of G, and I can look at f of G prime, okay? And I have a box, a multiplication in here. Well, we want these maps to preserve that. So we do that. Okay? So that's what a group homomorphism is. So again, a group is a set with extra structure. A group homomorphism is a function that preserves that extra structure. And now we can make a new category called group. Okay? The objects of the group, are all groups. And the morphisms of the group are all group homomorphisms. Okay. So that's a second example of something that of a category. It's kind of similar to sets. Okay, just here sets we just had like naked sets, and here we have groups. You think of groups as sets with more structure, and we want the maps to preserve the structure. Okay, let me give you some other examples. Now I'm going to give you an example from from linear algebra. Those of you who took linear algebra also have a good life. Okay, so we'll call it vect. There's another category called vect for vector spaces, and the objects of vect are all vector spaces. And the morphism of vect are linear maps. Okay? If you took linear algebra, you know about these things. They're just basically vector spaces are ways of talking about directions and lengths, and linear maps are ways of talking about changing directions and lengths, but in a nice way, preserving the structure. Okay. We're coming to more interesting examples in a second. Again, some of you might have seen this, some of you might not have seen it. Okay, so let me give you some more examples. Okay. There's a class that they offer here called Topology. Okay, and so we make a category of topological spaces. Okay? Basically, topology is like advanced geometry where you don't worry about straightness of lines, you worry about connectivity. Is that something? Okay, guess what? Top is a category. The objects of top are all topological spaces. And the morphisms of top are special types of morphisms that are functions between these spaces. We think of spaces as a set of points, but we can tell when the points are near each other. Okay? And the morphisms are what's called continuous maps. In other words, functions that preserve that closeness. If the topological space, you can tell when two things are close, then the morphisms can also kind of tell. Okay, good. So we have so far four nice examples: set, group, vector space, topology. Okay? I'd like to do an example that's totally different. Okay? Okay? So here's something that anybody, computer majors who took discrete structures also can deal with. Okay? This is the category N. N for natural numbers. Okay? The objects of N are all natural numbers. Okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. Okay? The morphisms of N equals, well, I'll tell you. Here's one natural number. Here's another natural number. There's a single morphism from this number to this number if and only if x is less than or equal to 1. So, there's a map from 5 to 7. There's a map from 7 to 9. Single morphism, that's it, one morphism. Now that's different than anything we saw before. Between any two sets, there could be a lot of different morphisms. Between any two groups, there could be a lot of different homomorphisms. Between any two vector spaces, there could be a lot of morphisms. But here, there's 1 or 0. Let me just say, from 7 to 5, there is no morphism. There's no morphism from 7 to 5. There is one from 5 to 7, but not from 7 to 5. Okay? Okay, let's just go through some of the requirements of being a category. Well, if there's a morphism from 5 to 7, that means 5 is less than 7. And there's a morphism from 7 to 9, that means 7 is less than 9. Then there's a single morphism from 5 to 9. Okay, because if 5 is less than 7, less than or equal to, and 7 is less than or equal to 9, then 5 is less than or equal to 9. So that's good. So that's the composition. Okay. And composition is associative. Why? Because what was the requirement for associativity? That two seemingly different things really are the same. Well, you only have one morphism between any two objects, so any two seemingly different things really are the same. Okay. Next, 7 has a special morphism to itself because 7 is less than or equal to 7. So we call that identity. Okay. And if you have a map from 7 to 8, and you have from 7 to 7, then that composes and becomes that. So the composition of this with this becomes this to this. Okay? So think of it as it's a category, but it's a very thin category because you only have one morphism between any two, at most one morphism between any two objects. You could have 0. Okay? So the natural numbers forms a category. Interesting. Let's do another example. The real numbers. By the way, this has an infinite number of objects. All of the examples that we have an infinite number of objects. That doesn't bother us. But let's talk about this. Here's another example of a category. The objects are all real numbers. Okay? Now this is hard to hear. I can start writing them, but this is a little bit hard. But you know what? Your 9th grade teacher did it the first day of 9th grade. He or she did this line. Okay? And basically, the objects are that. And the morphisms, well, if you have a number here and you have a number here, if one number is less than the other, then, so if you have a real number here and a real number here, there's a morphism from R1 to R2 if and only if R1 is less than or equal to R2.
Can I ask about that condition? Just, because obviously like in the natural numbers, I could define a map that sends n to n minus 2, right? But how come that isn't considered a morphism?
Okay, because, so there is a map. Well, what would a map from 7 to 5 look like?
There could be a few different maps, right? I mean, it depends on what operations we're allowed to use.
Right, but 7 is just a thing. It's not the set of 7 elements. 5 is just a thing. It's not the set of 5 elements. So there's no, our definition. Now, if you want, you can make another definition. You could talk about sets. You have a set called 7, and it's which has 1, 2, 3, 4, 5, 6, 7, and you have a set called 5, 1, 2, 3, 4, 5, and then you can have that. But that's not taking place in this category. That's taking place in the category of set. So if you want, you can think of this as just a shrunk down version of that.
What do these maps look like when I map 5 to 7? Is it just like
it doesn't do anything because
okay.
it's only either it's there or it's not there.
So there's no rule that defines the map element wise? Okay.
It's not 7 is not a set. 7 is just number 7. 5 is not a set. 5 is just the number 5.
Right, but I'm just thinking like I could have a map from the natural numbers to itself that just maps every number to one less than it, or it's half divided by 2, say.
So fine. So let me show you. Within the category, you got to turn. Within the category of sets, okay, There is a set called natural numbers. There is another set called natural numbers. Okay? These are two elements in the category of set. Okay? And there is a function called -2. Okay? So this would take the number 7.
Well, actually, that won't work because we're not mapping end to end. Zero's got no
Right.
image, right?
Okay, so we'll call it bounded set.
Okay.
Down bounded set. So it's going to take the element 7, and you take 7 minus with a dot over 2. Okay, and you look at the image of 7 in there. 7 goes in there, and you get out 5, which is an object in there, which is an element in there. Okay, but that's within the category of set. This is a different category.
Okay.
There's a line from Pointer A. It says mathematicians are people who give different names to the same thing.
Sure.
Anyways. Okay. So these two examples are much different than the other examples. Let me give you another example. Another example of a category. And lots of examples. And again, my goal here is not to teach you these things. Those things that you know, you know. Those things you don't know, you don't know. My goal here is to show you how category theory can deal with a lot of different issues. That's my goal. Okay. So I'm going to talk about the category called matrices. Okay. You all know, you took linear algebra, you know what matrices is. You took discrete structure, you know what a matrix is. Very good. So the objects of matrices is natural numbers. Again, natural numbers, not thought of as a set, just thought 1, 2, 3, 4. Okay? And the morphisms of matrices, well, I'll tell you what a morphism is. Okay? There are two natural numbers, m and n. The morphisms, there's a lot of them, are all m by n matrices. Okay? A morphism is an m by n matrix. A morphism from m to n is an m by n matrix. That's it. Okay? Now we have to go through the axioms, make sure it works. Okay, great. So, if you have an m by n matrix, hold on, and you have an n by p matrix, what can you do? So, if this thing corresponds to a particular n by n matrix, and this thing corresponds to a particular n by p matrix, what can you do with these matrices? You can multiply them, right? You can only multiply matrices when these numbers, the number of columns here is equal to the number of rows here. What do you get out after you multiply them? You get out an n by p matrix. Okay? So, the composition in this category corresponds to matrix multiplication. That's an amazing thing. Okay, that's an amazing thing. Matrix multiplication is associative. When you take three matrices, you multiply it like this, and you multiply it like this, and you get out the same thing. So it satisfies the requirements of a category. Great. What should be the unit? Well, there's a special matrix that goes from n to n. It's a special matrix that goes from n to n. Okay? It has 1 down the diagonal and zeros everywhere else. And guess what? When you compose that with any other map, you get back the identity. That matrix, composed with any other matrix, composition, matrix multiplication, is the same thing. It doesn't change it. So these identity maps you should think of as very stupid things. What's the purpose of them? They don't do anything. But you need them. Okay. great. Let me give, half of you are computer scientists, so let me give you something from computer science. Okay. In computers, you talk about types. Okay, so you have int and real and float and string and things like that. Okay, you can also have another type like float cross int. Okay, a floating point and an integer. You can also have something like this. You know, a name is a string, or let's say your address is an integer cross a string. The number of your house cross the name of the street that you live in. Okay, that will be it. Okay, so you have a lot of these different types. Okay, so let's talk about the category of processes in terms of computers. The objects are types. Where does data come from? Where does data go to? Computer people are very nervous about this. We like to type programming languages where your functions tell you what your input is and what your output is. Because if you have such a thing, you're not going to make a mistake. Okay? And the morphisms of processes are all computable functions that take in, okay, for those of you who speak object-oriented, you don't call them functions, what do you call them? The methods, right? Methods, yeah, let me the right lingo. Okay, those are computer functions that take a certain type, they take a certain type of input, and they output a certain type. Okay. This kind of has a feel of sets, right? Your types have all the type of information within each one, and then you have functions between one and the other. Okay. It's a nice way of thinking. Okay. Let me talk about a little logic, and then we have to move on. So we're going to talk about a category called propositions. Okay, propositions. What's a proposition? It's a statement that's true or false. All of logic works with these propositions. Okay? So let me tell you what the objects are. The objects are propositions. Okay? So P stands for whatever, Q stands for whatever. Okay, and now I got to tell you what the morphisms are. There's again one morphisms between the two, and not there's either zero morphisms or one morphism, but not more. So a lot of times our categories had many morphisms between things. Here we have only one or zero. Okay? There's a morphism from P to Q if P implies Q. So if today is Tuesday, that implies tomorrow is Wednesday. Okay? If it's raining, that means there are clouds in the sky. Okay? If you got a ticket, that means you went over 60 miles an hour. One implies the other. To make sure it satisfies the requirements. Okay? Well, if P implies Q and Q implies R, then P implies R. Okay? Logically. Okay, so you have that type of thing. And just for the identity, every statement implies itself. If today is Tuesday, then today is Tuesday. That's always true. If it's raining outside, then it's raining outside. It's true. Okay? So this brings in logic. Okay? I want to just talk about two other things in logic. We could talk about predicates. Predicates are also in logic, where you have not just true or false statements, but it depends on the input. So P of X, P of Y, things like that. So I'm going to talk about predicate with three. These are predicates with three variables, X, Y, and Z. Okay? And you could have Q with X, Y, and Z. Okay? And the morphisms, well, if X, Y, and Z, P of X, Y, and Z is true, then Q of X, if this implies this, then it works. It's just like that. Just this is baby logic. We only talk about true or false statements. These are statements that take an input involved. Okay, those are called predicates. Good. One more logic example. This is called proof. Proof. Okay? The objects are propositions. The objects are propositions, just like before. Okay? But the morphisms are not if one thing implies the other thing, but rather P, Q, tell me, is there a proof from P to Q? Does P imply Q? Is there a proof that tells you it is? Yes or no? Now, the point is there could be more than one proof. There could be more, as opposed to implication, there could be more than one proof. Okay? You can have a statement, you can have another statement. This statement, if you assume it's true, you can prove that this statement is true, but you could have more than one proof. Okay. So there's a lot more examples. I don't want to get them. I want to get to the second definition because we have 15 minutes. So I want to talk about the second definition. Okay. So the first definition was what's a category. The second definition is comparing categories. Okay. What's between categories. So that is definition a functor. F-U-N, it's sounds kind of like the word function, which it's supposed to. Okay? And this is capital F, and it goes from C, that's a category, to D. Okay, let me tell you what it is. It's kind of like a graph homomorphism. So let's remember what a graph homomorphism is. A graph homomorphism is a way of going from one graph to another. Okay? It takes an edge here to an edge here. It's going to take vertex here to a vertex there. Okay? But it satisfies certain requirements. So let's go through. Let's just go through what a graph homomorphism is. I'm going to come back to this in a second. Okay? So you have edges and vertices. That's a graph. You have another edge and vertex. That's a graph. Called E prime and B prime. That's a graph. Well, what's a graph homomorphism? It's a function that takes edges to edges, vertices to vertices, but they should match up. They should match up well. What does it mean, match up? Well, if there's an edge here from A to B called F, okay, then this function should go from F of A to F of B. In other words, the edge here goes to another edge here, but they match up. Okay, the functions respect the source and domain, source and target. Okay, I don't want to get into it, but a functor is the same thing. You have edges, you have morphisms in here, okay, little f's. It's going to go to capital F, little f. Okay? And you want them to match up nicely. I can get into it, but we don't have time. Okay? But we have other requirements too. Why? Because a category is not just a graph, it's got more structure. So one of the things we want is F of, let's say I have two maps in here, F and G. Okay? Well, I wanted to go to F of G, goes to F of I want, this is the composition in C, this is the composition in D. I want composition of things in here to go to composition of things in here. Makes sense. Okay, that's extra structure. Another thing I want that a functor has to do is, you know what? Let's say I have an object here called x, and I have identity on x. And this is in C. Okay. Well, I want, there's going to be another object here called f of x. That's where little object here, x, goes there, f of x. And you know what? This is going to be f of x, bam. It's going to be identity of f of x. Okay. And so I want the following requirement. Identity of f of x is equal to f of identity of x. In other words, I want the functor to preserve this identity maps. Makes sense? Okay, good. The rest of this talk is just examples, but what am I trying to do? I'm trying to show you that all these different things that we talked about the first half, they're related by these functors. Okay? And I want to tell you a little bit of the history of category theory. Category theory was started by two people. One was Samuel Eilenberg, and the other one, his name is Saunders MacLean. Samuel Eilenberg was a topologist. He was very much into topology, okay? And he liked shapes, etc., etc. Saunders MacLean was an algebraist. He was very much into groups and rings and stuff like that, okay? And what they were dealing with is taking shapes, topological spaces, and saying, okay, let's give them algebraic things to correspond to them. Okay? Let's give every shape an algebraic thing. So basically what they said was, you know, we have those shapes. They're elements of this topological space. And I want to assign to a space a group. So that's a functor like that. It takes a shape here and it gives it a group. Okay? But it should preserve all those structures. Okay, so you have two different people from two different areas of math, one topology, one algebra. They get together and they say, you know what? We have to talk about this thing called, let's invent this thing called category theory, which can talk about not only topological things, but also algebraic things, and it can relate them. So that's the whole purpose of category theory, is relating different things. That's what it started, and that's what it's intended, and that's the purpose here. Unifying concepts, to show that they're related. Okay, that's where we get. Okay, good. Let me give you some more examples of, so this is an example of a functor. Let me give you another example. Okay, you have the category of groups. Let's think about what a group is. A group is a set with more structure. Okay, a set with more structure. Okay, and the morphisms are functions with more structure. Functions that satisfy certain requirements. Okay. But we didn't like that. We weren't, not all of you knew what a group is, but you all knew what a set is. But you know what? There's a forgetful functor. It's called U, capital U. U for underline. Take a group. What's a group? A group is a set with a multiplication and a unit and this and that. And just forget about all that stuff and just think about the set of elements. That relates a group to a set. That's a nice thing. Okay? So you can do that. Okay? Let's talk about something else. So these are called forgetful functors. You forget the extra structure. Okay? Well, you have topological spaces. What did I tell you is topological spaces? It's a shape. You think of the points of the shape as the elements. Well, you can forget the set. You can forget the shape. You can forget what set, what point is next to another point, and just get that. Okay. And we talked about vector spaces. And I told you vector spaces are sets with operations that let you deal with direction and well, it lets you deal with directions. But you know what? They're basically, the extra structure is grouped with more operations, but you can forget those more operations. So we're making those connections between them. Okay, great. Let me give you some more examples of other functors. First, let me give you another example. Finite sets. Let's say I didn't want to deal with all sets because it's too much. I want to talk about finite sets. Okay? Well, finite sets are just like sets, but you only care about finite ones, not big ones. Okay? Well, there's an inclusion functor from finite sets into sets. Finite sets is a subset of all sets. Okay, so you can include them. Let me give you another one. Ready? The natural numbers includes into the real numbers. Okay, natural numbers, 0, 1, 2, 3, 4, 5. So I told you, the first day of 9th grade, your teacher went like this. He or she was talking about -1, 1, 2, all real numbers. Well, in particular, you have natural numbers sit inside that. So these two examples are called inclusion functions. Functors. Good. But there's a functor from the real numbers to the natural numbers too. There's actually two. There are functors from here to here. One is called floor. You give me any real number, I'll give you the floor of that real number. You give me any real number, I'll give you the ceiling of that real number. Okay, so floors and ceilings are examples of that. Okay, great. I want to go to logic for a second. There were two categories that we dealt with. One was called proof. The objects were propositions, and the morphisms were proofs that one thing leads to another. Here we had a simpler category. The objects were propositions, and one implies the other. There's a morphism from one to the other if one implies the other. Okay, good. There's a map here as follows. It's a functor. Look, the objects here are propositions, P and Q. Okay? They're the same objects, so one goes to the other. But look what happens here. If there's a proof from P to Q, then there's definitely P implies Q. If there's a proof from P to Q, then P definitely implies Q. So there's a map from P to Q. Okay. The shocking thing is, okay, this is the most shocking theorem of 20th century mathematics. It's called Gödel's incompleteness theorem. I'm waving my hands about some technical details. There are two propositions in here that one implies the other, but they don't have a proof. It's incompleteness. There's no proof that one implies the other. One implies the other, but there's no proof. Okay? So that's a statement of Gödel's incompleteness about these things. One more example, something from physics. Okay? I want to give you another example of a category. Take any group whatsoever, it forms a category. Okay? So